And then I can also help answer any comments in the chat that aren't directed to Igor or you that might be more MarsU related or some chat management, something like that. Yes.
Yeah, okay.
Yeah, this I was actually really fascinated. This paper here. There's a study. Let's see. So you know how we could use this these aerogels for hypervelocity particle capture. It was proposed to also use them to collect and capture and observe the properties of the dust in the Martian atmosphere. But the experiment never actually was proposed, but never launched and operated. Sounds like it holds a lot of potential too.
Yeah.
So should I try sharing the screen? It says that I cannot do it.
Yes.
You need to enable it.
There we go. Yes, good idea. You should be able to now.
Okay. Let's see. I'm going to try to. Can you see it?
Yes.
Yes.
All right.
Yeah, it was the Mars Scout mission was to fly, collect suspended dust in a silica aerogel collector, which would then be sent back to Earth.
Is that the paper that you sent me? The last one or
no? It's I can send you it. Looks like they have a reference here.
Okay.
It's raining buckets.
Yeah, it's raining a lot here as well. Where are you located, guys?
I'm in Chile now, but in the near Santiago, near the capital. This is the Central Valley. So
All right. I want to visit
it's not
sometime.
raining here.
Yeah, Chile is this amazing country in terms of how long it goes, right? From the north to south.
Yeah, we have every climate in the world in here, all the climates.
And it's so narrow, right?
Yeah. Have you been in here?
No. The only country in South America that I've been to is Peru.
Ah.
Yeah, we've gone to, my wife and I went to Cusco and
nice.
Machu Picchu, and that was cool.
Yeah. Yeah, nice place. No, Chile is totally different. Yeah, the people is different, and even the food is different because Peru is famous because of the food they have is amazing, and now we are not so amazing.
Oh, really? So what is food like in Chile?
Yeah, no, we are famous because of the wine.
Yeah, I think I've bought some wine from Chile. Yeah.
Yeah, no, we have. I live in the countryside near Santiago, and there is a lot of wineries here.
Very cool.
Nice. Just
yeah, everywhere.
Just admitted everyone, and Igor, I think as we grow as a university, we are open to discussing about having you maybe teach sometime.
Yeah, so as I said, that that requires an approval from the university because it's considered a conflict of interest. But you know, we can talk about it later if you so desire. I mean, you know, it's not something that I could do just like with a seminar. A seminar is considered, you know, a dissemination of research. It's not really so much teaching, but yeah, proper teaching is a different story.
Okay, sounds great.
So Priscilla, you're going to stay on video, I hope.
Do you want?
I do, yeah. I mean, it's actually very difficult to speak to a computer screen with any kind of enthusiasm.
Okay.
I mean, I can sort of try to do that, but it's always nice to see a face. I mean, I've been teaching on Zoom for a year, or I guess a year and a half almost. And yeah, there's a huge difference when people, when you can see their faces versus you can't.
Yeah,
and I know, you know, I know for you, you know, there's no difference. But oh, some other folks turned the videos on.
No, I think that also for the students is the same, because you can see your partners and what are they doing. So yeah, I think for everybody makes a difference.
I had a student who was sitting, and behind him was like a couch, and I think his girlfriend had like a big teddy bear, and it was constantly waving. Like you couldn't see the girlfriend, but you could see the waving teddy bear. And everybody was laughing. It was kind of a fun moment. But then they got a little bit too much, and I said, I have a question specifically for Gabriel's teddy bear, because it keeps waving at me. And I think that's when they realized that it probably wasn't a good idea to keep doing it. But yeah, you can have more fun. People, I think, can tune out a lot more easily when they just see the slides rather than other people.
Yeah.
Yes. Yeah. So everyone, feel free to turn on your video. Yeah.
So we're going to wait for a few more minutes, or when do you guys usually start?
We usually start a few minutes after.
Okay.
We can start on Priscilla's readiness.
Okay, so let's wait a few more minutes and then we can begin.
Sounds good. And where are you, Cole?
Just outside of the Washington, D.C. area.
Oh, okay, yeah. So that's not surprising then that it's raining for you, because I'm, you know, in Philly suburbs and close enough to have the same weather. Yeah, I think somebody commented about bandwidth limitation. Yeah, so fair point. But I've taught classes with like 70 people, so I don't think we're going to have more than that.
Those are my dogs. I'm sorry. There is a lot of horses here around in the back, in the next house, and the dogs are crazy because they have never seen a horse before, so they don't know what to expect or what to do. They just bark all the time.
Wait, you just moved into the house, or the horses just moved into the house next door?
No, there is I don't know the name. We have some neighbors that they have horses.
Yeah, but how come the dogs haven't seen them yet?
Because there is a fence that they cannot see to the other side. So
Okay.
it's just noise and a mysterious noise.
I see.
Yeah. Okay. So I think that we can begin.
That's good.
Okay. Yeah. So welcome everybody. Thank you to join us here to this new MarsU webinar. And today I have the pleasure to host the lecture of Professor Igor Bargatin about his work on levitation. And Professor, how are you?
I'm good. How are you?
Fine, thank you. So before we begin the lecture, I want to present Professor Bargatin. He is an associate professor from the Department of Mechanical Engineering and Applied Mechanics at the University of Pennsylvania. So please, Professor, you can begin when you're ready.
All right. Thank you, Priscilla, and thank you, Cole. It's a pleasure to be here. You know, I'm excited that there are now universities devoted solely to Mars, educating the future workforce for Mars, I suppose. And here I'm going to talk about the research that we've been doing over the last few years in my lab, which relates to Mars, but not just to Mars. It also relates to Earth. So hence the title, about levitating aircraft for Mars and Earth. And so I'm going to start by asking this question: how can we make true microflyers? And you guys have probably heard about microflyers before, right? Drones of various kinds, as long as they're small enough, are often called microflyers, which is a name that everybody accepts now. But if you think about it, it's a misnomer, because micro means something smaller than a millimeter, right? It should be on the scale of microns, whereas the microflyers that we can buy right now are, you know, maybe this big, a few inches. In fact, I collaborated with a colleague of mine who's made the smallest helicopter, or smallest rotorcraft, and they were about, you know, an inch in size, or the latest version a little bit smaller. So the question is, can we make true microflyers? You know, here's one example from Harvard, from Rob Wood's group. These are so-called RoboBees. Perhaps some of you have seen them. So these are flapping wing flyers that are actually tethered for the most part. They have a paper about untethered flight, but then they need focused sunlight. Perhaps they have even better versions now that they can fly just using sunlight. And here's the, can you see my pointer, by the way?
Yes.
Oh, excellent. Okay. So here's the smallest self-powered flyer. That's from my colleague Mark Yim at University of Pennsylvania, which is basically, you can think of it as a tiny helicopter. It's a rotorcraft with a rotating propeller, and it's just the size of a quarter roughly. So these would normally be called microflyers. Sometimes people use words like nanoflyers, but of course they're still very much macroscopic, many centimeters typically. And scaling below 1 centimeter has proven to be quite hard. A lot of people are working on it, but it hasn't happened yet. And there are lots of issues, especially after collaborating with one of the leading researchers in this field. Lots of issues with scaling down propulsion mechanisms, electronics, and putting everything together and then carrying enough power with you to actually be able to fly. And then, despite the fact that actually in nature, we see things fly that are really tiny. So these are true microflyers. These are very small insects that can fly around. They often have sizes down to about 100 microns. And a friend of mine actually studies them, and there's a paper here that talks about how they fly. So the question is, can we perhaps figure out how to make true microflyers, engineer true microflyers by using different mechanisms. And in particular, we decided to start with something that works very well at micro scale, at truly dust scale, right? So micron scale particles, and then try to scale it up. So I'm talking about photophoresis, which is translates from the Greek roughly as light-induced flow. Photo for light, phoresis for motion, and it's been studied for over 100 years, and works roughly like this. If you have radiation coming into, into a spherical particle, for example, then if that particle is dark, then the hot side will warm up. The side facing the radiation will warm up and become hot. And then it will create a net force that's acting usually in the direction away from the radiation. In the free molecular regime, when individual molecules are flying around all by themselves, you can neglect the radiation. For those of you who are more technical, that means that the mean free path between the collisions of molecules is much larger than the size of this sphere. So in the free molecular regime, it's very easy to explain how this works. You basically have a cold air molecule coming in, hit the surface, now absorb some of the heat and leave with a higher velocity than it came in with. On the cold side, that may also happen because it's also usually getting warmer. There's some heat conduction from the hot side to the cold side, but there's less of it. And so as a result, you have this asymmetry between the left side and the right side, and there will be a net force, therefore a recoil force that's pushing in this direction, right? Pushing to the right. And this happens again in the free molecular regime, which we characterize using Knudsen number. That's a ratio of the mean free path and the size of the object. So if it's over 10, then you have this picture. There's another regime where the Knudsen number is very low, which is called the Continuum Regime. And then in that case, you would actually have continuous flow. So photophoresis stands for flow. You would end up with a flow of gas around this sphere. So my point is, again, without getting into too much technical discussion about the physics of it, non-uniform heating causes gas to flow. Generally, it's going to flow from cold side to hot side, and there will be a reaction force that's actually pointing in the opposite direction. This idea has been around for a really long time. It's actually studied for many potential applications. Here's perhaps one of the coolest ones. This is a paper in Nature from a few years ago from, I believe, University of Utah, where people created a three-dimensional display. So kind of like Star Wars and Princess Leia. And in fact, I'm not sure. Yeah, it doesn't look like Princess Leia here, but they certainly reference Princess Leia, I think, in some of the talks. And you can see that this is done by essentially illuminating a particle that is suspended using these forces, photophoretic forces, and then moved around. And as it moved around in 3 dimensions, it's illuminated with different colors. And so as a result, if you can move the particle very quickly, you can raster through 3-dimensional space and create color images and eventually videos. At this point, I think it's not quite fast enough to do images, but to do videos, holographic videos, but they're definitely fast enough to do images. So there's a lot of work devoted to that. In addition, people have been studying photophoresis as a way to potentially keep the Earth cool. So some of the efforts on geoengineering have been looking at whether you can keep particles up in the atmosphere reflecting sunlight for some period of time. And these forces can actually allow particles to stay up in the very high layers of the atmosphere for very long periods of time, because the sun can push them up. So they'll go down during the day. Of course, tiny particles go very, very slowly. That's the difference between fog and rain. Rain goes down fast, fog either doesn't go down at all because it's getting blown around by winds, or it goes down very slowly. Anyway, so photophoresis has been studied a lot for really, really small particles. And what we're interested in is figuring out how to scale it up. There's another related phenomenon that some of you may be familiar with, and that's called Crooks Radiometer. It's a little toy that has been around for more than 100 years, and you can order it, you know, in a Amazon in the US, or you may see it in glassblower's shop. It's kind of a novelty item. You put it out in direct sunlight and it will rotate. And sometimes people think that it's light pressure that causes the rotation, but it's actually, which is understandable because it's called radiometer, but it's actually a thermal effect. Each vane has a black side and a white side, and the black side heats up, and then it's about a degree warmer than the white side. And then the molecules that hit the black side, they actually absorb the heat and leave with a higher velocity, a lot like in the picture that I was showing in the previous slide. So you get a recoil force, and it's pushing on the black side and makes the whole thing rotate. So it's a nice toy. You can use this force definitely to rotate something on a low friction. It works best if you use very low pressures, about 10,000 times, typically lower than the atmospheric pressure, maybe even 100,000 times, so about 1 Pascal. So this force also goes by different names, by the way. So it's called photophoretic, radiometric, sometimes even Knudsen force, and it's generally exerted on plates that have different temperatures on the opposite sides. Again, powers Crooks Radiometer. By the way, Crooks, it doesn't mean that, you know, it's a thief or something. It's a name of a person, right? Sir William Crookes was a famous scientist in England in the late 19th century. And he's the one that I think discovered it and developed some theory. So this force is, unfortunately, however, you know, it's about 100 times too small to make those paper veins fly around, levitate, right? It's about 100 times smaller than gravity. But what we've been able to do in my group is actually make structures that are as thermally insulating as paper, or perhaps even more thermally insulating, but also extremely lightweight. So in fact, a lot of the research that I was doing when I just started at the University of Pennsylvania was about extremely lightweight structures. So these are these plates, and I'll talk a little bit more about it, how they look and what they do. But that's the basic introduction. So if you know, when I started maybe 5 years ago, we started by making very thin continuous plates that were about 25 to 100 nanometers thick. They were made from freestanding aluminum oxide. So Al2O3 approximately, and we could make them big enough that you could put them on a macroscopic object, so they could be centimeters long. And for comparison, that's only about 100 atoms thick, and generally thousands of times thinner than paper, than plastic cling wrap, or household aluminum foil. So all of those things tend to be tens of microns, whereas we're talking about tens of nanometers. And our structures could not be completely planar. Like if you made them completely planar, they would curl up. Here's sort of a cantilever like shape. This one is corrugated, this one is not. See, it curled up. It's actually a lot like an ice cream cone in shape. And that's because of something called residual stresses that exist in very thin films. They will generally like to curl up. And so if you don't want it to curl up, if you want it to keep its shape, if you don't want it to deform under its own weight even, then you need to increase what we call its bend-in stiffness, its ability to maintain its shape and not bend. And we do it by using this honeycomb corrugation, where we still use a very thin material, but it's going up and down. So you can think of it as hexagonal cups that are connected to each other on top here. Okay, so the non-corrugated flat films typically curl up, but these ones do not. And of course, the corrugation tricks have been used to increase stiffness at the macro scale for a really long time. If you look at the insert of a chocolate candy box, which actually contains the candy, it's a lot stiffer than a planar film of the same thickness. Why is that? Well, because the geometry makes it stiffer. The corrugation in this case is actually pretty similar to what we're using because it also has hexagonal symmetry to it. And then what I call 2D corrugated sheets are used all over the place in construction. You know, the siding of most houses is corrugated. It's not a completely planar sheet, but rather something that is moving and has a profile to it. And that's what makes it stiffer, right? It makes it very lightweight, but also very stiff. And then there's honeycomb sandwich structures that are quite ubiquitous in construction, aviation, space, obviously, and even things like musical instruments. You will, wherever you need high stiffness and low weight, you will likely see sandwich composites. Okay, so what we created was a corrugated film, and in fact, probably the thinnest macro scale object. At least I haven't heard anybody correct me on that yet. Maybe there are thinner structures. But you know, these are big enough that you can hold them in your hands. Previous structures that have been made that are extremely lightweight. This one is from one of my colleagues, Julia Greer. And these structures are a little bit thicker than what we have used. You can see that they're also quite big. You can put them on an end line. And then things that we're all familiar with are, you know, soap bubbles. Soap bubbles can vary a lot in terms of their thickness. You can get some idea about how thick they are from the iridescence. That's an optical interference effect. And typically they're on the order of hundreds of microns. The fact that you can see iridescence means that it's on the same roughly thickness as the wavelength of light. Once it gets thick enough, they become kind of glassy. They don't have iridescence anymore. And if they become very, very thin, they become invisible. So the soap bubbles vary a lot in terms of their thicknesses, but typically from about 1/10 to 1 micron. Even thinner bubbles tend to pop very quickly because they evaporate. So our plates weigh as little as 1/10 of a gram and can float in air like mist or smoke because they are lighter than soap bubbles, even the thinnest soap bubbles that you can make. And I have a little video of that. I hope that works. Can you see the video? So there's a little plate here that is floating around, and we're not blowing on it. It's just catching the ventilation currents that exist in the room, right? So wherever the air is moving due to a HVAC system in the lab, that plate is going. So it's kind of fun to work with them because they can move away from you. And in fact, the students who were working on it at the beginning were telling me stories that, you know, they made a structure and it floated away from them, which sounded a little hard to believe until they made that video. And then the other structure that we made more recently, that was a couple of years ago, is what we call nanocardboard. These are closer to sandwich composites. These are structures that have two surfaces, kind of one surface on one side, another on the other, and there's a bunch of channels connecting them. So these are a lot like honeycomb sandwich composites that are used a lot in aerospace, but we made them at the nanoscale, and we made them in fewer steps, primarily because we cannot glue things at the nanoscale, right? The usual sandwich composites are often glued together or maybe brazed or some connected in a very kind of macroscopic fashion, but any glue has a much bigger thickness than the things that we would want to glue. So that's not a good idea. So we had to figure out how to make a structure that has what we call this webbing, this connections between the two surface sheets, as well as the surface sheets. And so If somebody's interested, I'd be happy to talk about the fabrication process, but we did it, right? And so we created structures that had a thickness of 50 nanometers or so, and had a height. It's a hollow structure, right? Had a height, which is shown here, which is between 3 and 50 microns. So it's a very hollow structure and has a density of about 1 gram per square meter, which again is much thinner than paper. Paper would often be on the order of 100 grams or so. But in this case, we're talking about very, very lightweight material. And by the way, this material can actually recover from extreme bending deformations. In particular, in this last video that is coming up, you will see that it can do things that a regular sandwich composite is generally not able to do, which is to survive a buckling deformation and then basically come back to its original shape. That you will never see at the macro scale. Things delaminate and fracture typically, but in the nanoscale, they can do it because of a process called reversible buckling. So again, I'll be happy to talk about it, but let me get to the levitation. Once we've created nanocardboard, we realized that we can actually use these radiometric or photophoretic forces to explore the ideas of levitating these plates. And what we started out with are some experiments at atmospheric pressure. So here you can see one of those plates. And what it's doing is it's floating above a glass slide. Here's a penny for comparison. And here's a side view, basically the same kind of structure, but looking at the side, you see that there's a gap there between the reflection and the actual plate. That gap is maybe 1/3 of a millimeter, maybe 1/2 millimeter. But it's essentially a small hovercraft. If you think about hovercrafts that can be used on land or on water, the way that they work is they pump gas beneath themselves, creating an air cushion, and then they float on that cushion. That's exactly what's happening here. Air is pumped below the plate to create an air cushion, and that mechanism, however, is related to photophoresis. Turns out people have studied it for a long time, also with a different name called thermal creep, where if you have a temperature gradient, remember in the photophoresis, you have hot side and a cold side. Here, you also have a hot side and a cold side. If you have it, the gas will float generally from the cold side to the hot side. And in this particular case, we have an LED. We have a carbon nanotube layer that's absorbing the light, and it gets hotter. Again, it's only about 1 degree temperature difference, so it's not a huge amount of difference in temperature, but it's enough to drive the flow of gas, and it's creating an air cushion. It's pumping air beneath it, just like a regular hovercraft would. Okay, so I can probably skip some of the technical details about how these work. And in midair, by the way, the same mechanism, if you particularly go to reduced pressures, can create something that looks a lot like a jet. So it's going to create a circulating flow, and there'll be a reaction force pushing up. That can be done in principle at any scale from millimeters to meters without any moving parts, right? So think of it as a small helicopter that creates a jet of air going down. But in this particular case, there are no moving parts. It's all thermally driven. You just need a temperature difference for it. So let me show one video of levitation. This is from our earlier paper. You can see that it's not very well controlled, but there's a piece of our nanocardboard that is taken off and kind of floating around a little bit in a small vacuum chamber. It's kind of like a jar that we used at the beginning. So since then, we've done a bunch of more experiments. And one thing that we did is we said, hey, we want to understand how this nanocardboard levitation works. So maybe one thing we can do is we can use nanocardboard instead of paper in a radiometer. So instead of just using paper painted black on one side, we can create something similar out of nanocardboard. And so a bunch of the talented students in my lab worked on it. And so they created something that looks a lot like radiometer. And because we wanted to test whether it works in atmospheric air, you didn't even need to put it in a vacuum chamber. So this is a vacuum chamber. It's a sealed glass jar. But in our case, we could just experiment with it in the lab. And the question was, could we make it work at atmospheric pressure? And of course, I wouldn't be showing it to you if it didn't. You can see it here, which just, the LEDs of 2 phones providing the light instead of sunlight. We don't get any sunlight in my lab because it's in the basement. But I'll show you some video of this working outside. So this incident optical power is about the same as what you get from natural sunlight. And here's the video outside my lab in the courtyard. And what we did here is we put a little jar. It's actually a peanut butter jar from one of the people in my group. We put a jar on top of it to just protect it from the winds, right? Because that can make things rotate as well. And that's a confounding factor. So we wanted to get rid of it. And so we put it on top. And in this case, it's just getting driven by natural sunlight. So it's not going down, it's not going around super quickly, as you might see. Like the linear velocity is maybe on the order of centimeter per second, maybe even a little bit less. But the interesting thing is, well, first of all, if you use paper, you get nothing. There'll just be no movement at all. And then even in our theory of how the nanocardboard is supposed to work, it's actually predicted to work even slower than what we're observing, maybe 5 to 10 times slower. So we were very happy to see this relatively slow movement because it's a lot faster than what our theory predicts. So something is interesting about the interaction between the veins of this nanocardboard and the gas molecules that we don't quite understand, but it's a good kind of misunderstanding that actually makes it work better than we thought. Okay, so here's a little graph that shows the rotational speed of this type of radiometer. We also did a whole bunch of simulations trying to figure out whether we can explain it, and the short answer is we could not, at least not yet. But again, it's a good kind of surprise where things are working better than you expect. It's a good problem to have when you're a scientist. You don't understand why something works so well. Okay, and then another thing that I want to talk to you about is more recent levitation experiments that were published this year, which use thermal accommodation, which is a type of surface property that tells you how well the heat is absorbed when the molecule hits the surface of a plate. If you have a very low thermal accommodation coefficient, then basically it bounces off more or less elastically without absorbing any heat. Whereas if you have high thermal accommodation and you have a hot plate, the gas molecules absorb a lot of heat. Okay, and thermal accommodation coefficient can vary between 0 and 1. 0 means no energy transfer, 1 means full temperature equalization between the gas molecules and the plate. So what we did is we actually made some plates made out of mylar where we put carbon nanotubes and they form this hairy surface on the bottom. We call it shaggy carpet sometimes. And what it does is actually traps the air molecules. So as they go in, they are likely to bounce around a few times before they can get out again. And every time they bounce, they absorb a little bit of heat. So that means that they're probably going to thermalize. They're going to reach the same temperature as our structure. And this came out in Science Advances earlier this year. So this just shows the structures that we made. And here are some screenshots from the video, but I can actually show you the actual video. Here's a little mylar plate in a much bigger vacuum chamber that is not curved, so it's actually easier to see what's going on. And here's my favorite video, I think. Oh no, that's not my favorite video yet. I'm going to show you my favorite video in a second. So what we did here is we created an LED light trap where we actually made sure that our structure would fly around without getting out of the vacuum chamber and for a while. So we created a system of 8 LED arrays and used a transparent mesh as a launch pad and clear acrylic vacuum chamber. So that created this kind of trapping light beam of a donut shape, and our structure would be trapped in the center of this ring. So here's my favorite video. We call it the Tango because there are 2 of these now, and they're kind of dancing around each other. They're both levitating, and sometimes they get a little closer, and then sometimes they move a little bit further from each other. Okay, so these are our basic results about photophoretic levitation at the macroscopic scale. Again, I mentioned that photophoresis had been studied a lot for basically dust particles, really, really small things. But what we're trying to do is we're trying to move from that micron scale to things that would be useful. You know, maybe centimeters, maybe between maybe millimeters and above, right? So there are different purposes. You could want to make a really small microflyer for Earth applications in particular, or you could make something that's very big and flying in the upper layers of the atmosphere. So one thing that we proposed recently is that you could use them to study the Mesosphere, which is a part of the atmosphere where nothing can fly. It's too high for airplanes and balloons, and it's too low for satellites. So only meteors burn up there, and then the rockets go on their way up or down, but nothing can actually hover in there. And we show that basically with these structures, you should be able to carry payloads that are a few milligrams, which doesn't sound like a lot until you consider what's been done in the electronics space recently. People have created all kinds of interesting sensors and power sources at this mass scale. So a cubic millimeter of silicon is going to weigh a few milligrams. And so it's possible to create what are called smart dust sensors. They could be doing gas sensing, they could be doing imaging, magnetic field sensing, acceleration, and they can be even integrated with communications and power electronics, all in a very small volume. Here's a reference that's showing a 1 cubic millimeter system that actually includes power, communications, and sensing capabilities. So we think our microflyers could be a perfect carrier for these types of sensors. And then another thing you could do is you could adapt these for Mars. Mars has an atmosphere that's roughly equal on the surface, I should say, on what would be called, you could call the equivalent of the sea level on Mars. It would basically have the ambient air or ambient atmosphere roughly similar to what we have on Earth at the altitude of about 35 kilometers. And so, these are roughly the same altitudes and pressures that we're working with. So you can imagine having these microflyers driven around by either laser beams or sunlight. There's less sun on Mars, but there's still quite a bit. And you could have these structures move around just driven by sunlight and collecting information on Mars. Especially if you go up to the higher altitudes, sometimes they're called highlands on Mars, or the highest mountain on Mars, which of course is Olympus Mons, is like way taller than anything on Earth. Those would be the altitudes where probably nothing would work. So we're all happy about the Mars helicopter Ingenuity, making multiple flights now, but I think going up in altitude is going to be pretty challenging on Mars because it's already pretty challenging to fly in the very thin atmosphere that they have that they're using right now. Okay, So that's pretty much it. I think that ran a little longer than 30 minutes, but I'd be happy to answer questions.
Well, thank you very much, Professor Bergatin, for your lecture. This is an amazing topic, and of course, it will have a lot of applications in the future. We already know that we can fly in Mars, so probably we are going to levitate in the future. So great news.
Yeah, so I think, you know, we're all very happy that we can fly on Mars. But for now, at least, we cannot fly on Earth in the mesosphere, right? So sometimes that region is called near space, and it's very hard to study because you cannot stay in there for a really long time. People send rockets, sounding rockets, they're called, but that's, you know, some minutes of flight during which you can collect some information about that layer of the atmosphere. So hopefully we're going to change that going forward, providing new approaches not only for other planets potentially or heavenly bodies, but also for Earth.
Yeah, we have a lot of things to understand in our own atmosphere. So this is a great application. So I have one question, then I am going to the audience, but let me see. I was curious about this levitation process because I was thinking about the mesosphere. And in the mesosphere, you have a decrease of temperature with height. That could affect in some way the levitation?
Right. So there's a complex dependence on temperature in the atmosphere, right? Going down, then up, then down again, then up again. Yeah. So lower temperatures actually are helpful for a mechanism like this, because what you're doing is you're utilizing the temperature difference between your plate that's levitating and the ambient air. So if you have, you know, if you're at about 90 kilometers, I think that's roughly the temperature minimum in the atmosphere. The coldest place on Earth is actually not Antarctica, but being up in the upper layers of the mesosphere. And that, you know, that means that you're, you know, below 200 Kelvin potentially. And so you could have a very large temperature difference between something that can absorb sunlight, which of course is more intense once you get above the clouds and above the lowest layers of the atmosphere. You start getting about 1,300 instead of 1,000 watts per square meter. That can heat up a well-designed structure to 400 Kelvin, potentially even more, versus, you know, about 200 Kelvin in the environment. So that gives you a roughly a factor of 2 temperature difference in absolute temperature. And that's very helpful for creating thrust. In fact, you can show that this structure will be as efficient as you can possibly be using sunlight, because it's going to be reaching efficiencies of about 50% converting sunlight into the kinetic energy of the gas. And, you know, jet engines are usually not more efficient than that. You know, roughly the efficiency of jet engines is at, you know, maybe at best 50%. And so that means that you're doing as best as you can using just sunlight to levitate.
That's great. I was curious because you in the publication, you also mentioned that your experiment uses like 5 times the sunlight to make the disk levitate. But then you show the video and yeah, of course, this also works under the radiance of the sun.
Right. So, so, you know, in the lab, actually, that goes back to your previous question. We don't have, you know, 200 Kelvin environments. We have 300 Kelvin environments. And they're very hard to create, in fact. So in the lab, we kind of have to add more light to compensate for the fact that our temperature is a little different from what it would be in the mesosphere.
Yeah. And I have one last question. This is the last one. This is a wavelength, an special wavelength to make it levitate, or it doesn't make any difference?
So we're using carbon nanotubes, which are broadband absorbers, right? They are black. In fact, some of the blackest paints have been created using carbon nanotubes. I think there's one that's called Vanta, if I remember correctly, which is made from vertically aligned arrays of nanotubes. And those can absorb, 99.9 something percent. And they look like a black hole, like it's eerie, right? If you look at the pictures, it looks like somebody has cut out in the image processor later on, but it actually is so absorbent that it doesn't reflect anything. So it has this really weird look. So carbon nanotubes are very good black paint. And what we're using is we're using them as a very lightweight black paint. And therefore, it's not particularly sensitive to the type of wavelength that you would be using.
Oh, that's great.
And that's, well,
Sure.
that's, if you used laser instead of sunlight, then you could probably play additional games with the absorbers that are more narrow band.
Yeah, sure. No, great. So we have some questions. First, I don't know, Cole, do you want to make any question after we begin with the audience?
We can start with the audience, thanks.
Yeah. Okay. So AC says, can you predict the efficiency of the system when using different gases such as H2 or helium versus something heavy like xenon, for example, or CO2 like in the Mars atmosphere?
Yeah, it's possible to, change the parameters in our model to predict the behavior in different atmospheres. We've been focusing on air so far. We also can do experiments with CO2 in a vacuum chamber, which would mimic the Mars atmosphere. But in general, all the mechanisms that I described, they work similarly. There's going to be some changes in the coefficients and the lifts, but it's generally probably going to work better with things like hydrogen or helium. But then again, if we're thinking about Mars and Earth, that's probably not very relevant to these applications.
Okay, thank you. Ivo, I think I pronounced your name correctly, says, could you briefly describe the fabrication of the thing? Thanks in advance.
Let me see if I have a, do I have a backup slide that I could show about? No, I think I'm just going to show this and talk about it again. So the way it's done is we use a special kind of silicon wafer that's used in microelectronics fabrication. It's called silicon on oxide, SOI. And we create discs basically of this shape that are about 3 to 50 microns thick of silicon. That's the first step, just the disc of silicon, 3 to 50 microns thick. Then we go ahead and etch some trenches, corresponding to this pattern here that we call the basket weave pattern. And that creates a hole in the disc. And then comes the magical step when we put our disc with these trenches etched into it, that go all the way through the disc, I should say, into an atomic layer deposition chamber, which deposits material aluminum oxide everywhere. It goes on the top surface, it goes on the bottom surface, and it goes inside the trenches, depositing on the vertical walls of those trenches. So now we have a silicon mold, as we call it, with a thin film of aluminum oxide on it. And so all that's left is we etch away that silicon. You can put it in a special etching tool that's called xenon difluoride, and it will go in and preferentially etch silicon while leaving the aluminum oxide alone. And eventually you end up with this hollow shell that is just made out of aluminum oxide with all of the silicon gone. And in fact, at the recent Materials Research Society meeting in the spring, it was all online. There's a group at Harvard that kind of followed our idea and took it a little further, where they made even bigger structures of nanocardboard using a similar process. But so far, they all have been used on microfabrication tools.
Okay, so Ron, do you want to make your question? You can turn on your microphone.
I just was wondering about the energy absorption limitations or range that you could have with these kind of devices or these pieces.
So when you say a range of energy, does that mean wavelength or
I was thinking more of a power level,
okay,
per square meter kind of thing.
Got it, right. So the incoming light intensity. So we've done experiments in our lab with light intensities up to maybe 10 suns, so 10,000 watts per square meter, about 10 times what you would get on a clear day. And they can generally handle it. Going higher is difficult in a lab because it can potentially be unsafe, and you probably need high power lasers as your source. But the things that we have observed is that if you don't control your structure very well, it can start curling up. I think that was obvious in some of the videos that I was showing. So that's definitely something that we're working on, how to minimize the curling that can be induced by thermal stresses at very high intensities. So that's the main thing that happens. I hope that that answers your question.
Okay, so AC, you want to turn on your microphone? Seems that AC. Well, I'm going to set the question from AC. It says, can you substitute graphene for the carbon nanotube light absorption?
Yes, I think you could. In fact, we've done some work. I had a talented postdoc in my group who did some work on light absorption in graphene. He has since, however, become his own professorship. He's at the University of Alabama right now. But it's easy to buy carbon nanotubes. Buying graphene is a little more complicated right now. So we just buy solutions of carbon nanotubes and deposit them rather than growing our own. And so it's just been more convenient to use carbon nanotubes, but I think you could very well use graphene as well. What we care about is how black it is and how lightweight it is. So again, we want really lightweight layer of black paint. And it's possible that some forms of graphene can do even better than what we're using right now.
Don't worry, AC. Let us know if you have any question. Cole, you can turn your microphone.
Oh, Edgar, I was just wondering if we could use this for heliophysics and monitoring the sun, since we could absorb up to 10 suns, the energy and heat.
Yeah, that's a good question. I think for this mechanism to work, you kind of want to have some gas molecules around, right? So I'm not a sun physics specialist at all, but my understanding is that if you get so close to the sun that you're, in contact with ion particles that are floating around, you're probably at thousands of degrees and so or more, and everything is going to melt, so and ionize. So my initial guess is that would be pretty tricky, but you could probably explore other heavenly bodies that have thin atmospheres. In fact, places like Triton, I think, have very low pressure atmospheres that could be explored using flyers that use this mechanism as well. But, I think Mars, and particular high altitudes on Mars, could be the best fit to this type of flying mechanism, because I think it's going to be pretty hard to push the rotorcraft, which is what Ingenuity is doing right now. I think it would be hard to make it work at an atmosphere that, say, is 10 times thinner than what they use right now.
Yeah, and the wind is a huge problem also, not only on Mars, also here on Earth, to this type of device.
Yeah, and no, that's a great point. And I think the first thing that we actually are proposing to study these, if we can make them, in the mesosphere on Earth, is to actually study the wind and then eventually temperature distributions. So you could actually release these and then observe how they spread out and track them by, you could either use very small radio transmitters, or you could even try to detect them using something like LiDAR passively, right, without anything transmitting from them.
Yeah, I think they are great tracers. You can see what is going on in the atmosphere, and maybe clouds. I don't know, because
so generally
don't
it's
know
above
a lot about the clouds.
Yeah, there's special kinds of clouds that exist in the mesosphere. They're called noctilucent clouds, or I think they're called polar mesospheric clouds. Evidently, you can see them sometimes at sunrise or sunset if you're far enough north, or south for that matter, actually. Above certain altitudes, I forget, maybe 60 degrees or something, you start to see these types of interesting cloud formations. If you search Wikipedia for noctilucent clouds, so polar mesospheric clouds, you'll see a bunch of cool videos. And I guess people are still trying to understand how they form, whether climate change is affecting them. These are all very interesting scientific questions.
Yeah, they can provide a lot of information also in the climate change. So yeah, we need to study our atmosphere in detail.
Yeah, in fact, I heard that the biggest temperature change is actually happening in the mesosphere due to climate change. And in fact, it's a cooling process. So the mesosphere is getting, the upper layers of the mesosphere are getting colder as the surface is warming up.
Yeah. Well, everything is a chaotic processes in the atmosphere, so there is a lot of things happening there.
I guess that's your specialty, Priscilla, right? I think I found one paper where you're focusing on not geo, I guess, planetary simulations.
Almost.
I should mention, regarding Mars, actually, there was one thing that's related to what I was talking about. There's a researcher in Germany who was looking at thermophoresis and photophoresis. They're related effects. One is just due to temperature difference, another one is due to light. And he was arguing that basically the atmosphere on Mars gets absorbed in the regolith and then released on a daily cycle by a pumping action that's very similar to what I just described to you in some of these hovercrafts. If you have a temperature difference, there's this thermal creep flow. And so what he was saying is that you would have this movement basically during the day when the surface layer of the regolith is very hot. You would actually have trapped gas move out into the atmosphere. And then at night, when the regolith top layer becomes very cold, you would actually have the opposite. The atmosphere is driven inside the regolith and can stay there overnight. So that's not something we ever see on Earth because our atmosphere is much denser. But Mars probably, and it's never been tested, but based on very well developed theory, probably has this unusual breathing cycle where the atmosphere is getting absorbed and released periodically.
Yeah. So AC have another question or comment. It says that using something like light tweezers could multiply of the nanocardboards with, say, intercalating surface be assembled while levitating into larger structures?
Great question. Yeah, in fact, I have multiple students, in particular summer undergraduate students, working on exactly this problem in my lab. We had our kickoff lunch for the summer program today, and they're all very excited about figuring out ways to create three-dimensional structures out of nanocardboard that could fly more effectively. In particular, we're interested in making things that would fly here on Earth using just sunlight. So we think it should be doable based on simulations, but of course, the proof is always in the experiments.
This is learning a lot. Remember reading your publication, and you mentioned we could potentially fly indefinitely. I was wondering how long these nanoplates could fly.
Yeah, so I think the question is, how long is the sun on for? And if you're in particular in the polar regions, right, if you want to study these polar mesospheric clouds, for example, then during the polar summer, the sun never sets. So you could fly as long as the sun is up. You know, here, say in Philadelphia, where I am, we never get polar day, but we get sunlight, for about 12 hours. And at night, it's possible to design structure. I think it should be possible to design structures that can actually rise during the day and then descend at night. And so they would actually oscillate in altitude, but always stay up. So this is speculative, right? I mean, we haven't really done any experiments in the mesosphere. So far, we only are doing experiments in a vacuum chamber in the lab. But based on theoretical models, something like that should be possible.
Very, very interesting. Yes, Katerina. Also curious how far we could image the surface of Earth and planets from the mesosphere and similar altitudes.
Yeah, no, it's a great question. What you could use them for? I think given the low masses, perhaps imaging is going to be challenging. You need a camera that's extremely lightweight, and despite all the progress with things like cell phones, they're not in the milligram scale yet. Maybe they will get there eventually. But you could do a lot of other things. You could study the temperature, you could study the humidity, you could study the concentration of different gases. So I think there could be a lot of science applications for something like this. And then once I think what I'm hoping to do is, get people excited about using photophoresis as a flight mechanism, get more people working on this, and eventually figure out the best ways to fly using photophoresis. And then once we get something into the mesosphere, I think new applications will show up, right? I mean, when the Wright brothers were developing the airplanes, or the Montgolfier brothers, they couldn't imagine all the applications that would ultimately be developed for balloons and airplanes. So I think it's important to get the ball rolling, right? It's important to get something working, and then I think it can often feed on itself.
Awesome. I have a few more questions here. Very curious. I was wondering if we could apply photophoresis to most aircraft and airplanes.
So aircraft and airplanes, at least for now, are way too heavy for something like this. Although I've spoken to a colleague of mine who was saying that there may be applications in terms of like reducing drag and modifying the boundary layers on the wings using sunlight-driven photophoresis, for example. But these are all very kind of speculative ideas that we're briefly talking about. So there may be, not in terms of replacing propulsion, that would be kind of hard to do, but in terms of maybe modifying some aspects of it that are quite important.
Awesome. We're excited and can't wait to read more about your research. Is wondering how large of a payload we could lift with these.
So right now it's milligrams, right? So it's about a cubic millimeter of silicon chips, whatever you can fit in there. I think eventually we can probably create bigger structures that will weigh, that will lift, you know, grams or maybe up to a pound. Because the atmosphere is so thin, even if you're very effective at creating a jet, you still need a lot of area to create enough lift for, let's say, a human being, right? And so I think it's going to be possible to increase the payloads from the milligrams to grams and maybe hundreds of grams, but I think it's going to be hard to go in, you know, unless you're talking about really gigantic structures. I think it's going to be hard to go much further than that. But, you know, who knows? I think we'll have to try and see and figure out, you know, what geometries are actually the most efficient ones and generate the most thrust. So we're actively working on that in my lab.
Nice, nice. Yeah, this very interested in Venus too. It is around 2.6 times the solar radiance in the atmosphere. I was curious to hear your thoughts there as well.
So Venus has enormously dense atmosphere, right? So it really depends on what altitude you're thinking about. Something like this, at least so far, we've made it work, you know, corresponding to the mesosphere pressures, so somewhere between, you know, 1 and 100 pascals. We're hoping to modify these structures, make them three-dimensional in particular, and make them work at atmospheric pressure, right? But then Venus is another factor of 100 denser. So, you know, that becomes an additional challenge. On Venus, the atmosphere is so dense that perhaps, you know, it's going to feel more like swimming for any apparatus that can actually move its wings or fins. So it may be possible to move around a lot easier than it is on Earth, and definitely a lot easier than on Mars.
Oh, very interesting. I have to look more into that one. There's two more questions here. Maybe what is it? Will be a rough cost estimate currently, and maybe 10 years from now for for manufacturing these plates.
Yeah, so, you know, generally if you go by the cost of fabricating microchip circuits, if it still has to rely on that, those are typically, you know, a few $100s for something that's about this big. But we're working on making these out of thin mylar, and then the cost could be much smaller than that. But of course, you know, if you want to study the mesosphere, for example, the current competition is from sounding rockets. And sounding rockets, I think, are on the order of $1 million per launch. So even if you cost hundreds of dollars, that's like orders of magnitude below anything else, although the capabilities are quite different, obviously. So it's not exactly a fair comparison.
one of the last questions here, I think, to encourage you to make some bold predictions. Is wondering how many nanocardboard plates would you and your team like to fly on Earth and Mars by maybe 2030 and 2050?
Yeah, so we really want to make. I mean, we're making, you know, tens per month right now, because we're figuring out ways to like assemble them, and in the process they sometimes break, so you have to have a bunch to work with. What we're hoping is to create, you know, new types of sunlight-driven microflyers on Earth, you know, things that could fly around using just the sun in the air around us, and really small robotic structures. So if we can do that, then I think there will be a significant market for it. If we cannot do that, then I think the biggest market would be things like, you know, mesospheric science research, which is a much smaller market, because everything, you know, science related is often done kind of once, right? And then you get the data and you're happy. So in that case, there'll be, you know, smaller, but even still much bigger than what we are right now. I hope that answers your question. I'm not sure that's bold speculation, but you know, I'm just excited about the research and figuring it out, because it may well be that nanocardboard maybe is not the best way to do it. Maybe we'll find another material that can do it even better, in which case we'll focus on that, right? So I'm not necessarily wedded to a specific type of material. I just want to make things fly without moving parts.
Nice. Nice. Sounds like maybe thousands one day, maybe tens of thousands plates. Well, I think we'll also have to consider more about the commercial potential. Sounds like.
Yeah, exactly. Right. No, I mean, if we can make flying structures that are, say, 1 centimeter, sunlight driven, then I think there could be applications of, you know, just making things fly around us and collect sensor data or other type of information, just like we use, you know, small drones now. That's obviously a much bigger numbers than scientific research.
Another question. Hello.
Yes, please.
A few thoughts. I'm wondering if you can do some kind of remote reading out of data. So for example, you put litmus paper on the bottom side and shine different colored lasers and you get different colors back. And
oh, I see.
You know, could you sense different, could you get something that would change color with different gases, pollutants, whatever, and then remotely read it? So you don't really need any mechanism on board to do the sensing.
Yeah, that's a great question. I think it should be possible, especially if you want to create something that is controlled by a laser beam. It makes sense to do remote sensing with that laser beam, right? So you could create something that would, let's say, either reflect or not reflect, either scatter or not scatter that laser light, depending on something in the environment. So I think that's definitely something we're thinking about, and it could be much lighter than, you know, full-scale electronic chips with all their power needs that you could put on these structures.
Okay, and I'm wondering how you would actually control it with a laser beam. You know, would you shine the laser on the left side of it and make the left side have more lift and therefore it turns right?
Yeah, exactly.
How far away you can't do that?
Yeah, so there are two analogies that I like to think, at least as far as just plate structures are concerned. Again, we're thinking about three-dimensional shapes, and this is, you know, I'm not going to tell, you know, what exact shapes we're thinking about for now, because it's all very much in flux. But if you have a plate, then there are two things that we're already familiar with and we know how to control. One of them is a parachute, which is kind of like a plate with a bunch of threads hanging down. And another is a helicopter. And both of those structures you can control by tilt, right? So you tilt the rotor of a helicopter, it's going to fly horizontally. If you tilt the canopy of a parachute, it's also going to start shifting horizontally in addition to just dropping vertically.
Right.
And so you can do similar things because it's creating a jet. If you tilt it, it's going to create a force that's going to be sideways. And so it's going to start moving. And in fact, our light trap uses that principle, right? So this bunch of LEDs that create a ring-shaped beam of light, they use it because when it gets to the edge of that ring, or actually gets from the center to that ring, the side of it that's closest to the ring gets hotter and it tilts, and that tilt actually moves it back towards the center. So that's how we can prevent these structures from escaping from the center of the vacuum chamber where we want to observe them for a while.
Yeah, sure. I think what you really want is to get them to follow a laser beam. So it'll like a cat will follow a laser pointer.
Exactly right. So
maybe you can shape the laser beam to
you can create kind of a donut shape with a laser beam as well.
Yeah, well, but I'm trying to picture you have a ground-based laser and this thing is up at, tens of kilometers up in the air.
Oh, I see. No, when I think about laser guidance, I'm just thinking about applications here on Earth usually. So not tens of kilometers up. It's possible to think about Mesosphere as well.
One more question. I'm worried about safety and pollution. If you release a bunch of these in the upper Earth atmosphere, some of them are going to get away from you and fall to the ground. And
oh yeah.
What happens if somebody breathes one in in their nose?
Yeah, no, that's a great question. So aluminum oxide is considered biocompatible material. People implant things with aluminum oxide. If you breathe it in, I'm not sure how damaging that could be. It depends on how sharp, I guess, it is and how ground up it is exactly. But it's a good question. My guess is that it's not going to be any worse than breathing in sand. But
yeah,
we haven't done the experiment, so we don't really know. And definitely we're not at the volumes where this would matter.
All right, thank you.
Thank you.
I think there's most of my questions over here. So if anyone else has anything, feel free to.
I think there's one in the chat also asking about infrared radiation from the ground, whether that can provide sufficient energy to give some provide energy for levitation at the atmospheric altitudes. Yeah, it's a great question. Yeah, there's definitely infrared, and it can potentially be used. There's about 300 watts, I believe, of long wave infrared coming from the Earth all the time. The question is whether that's going to be enough to make you warmer than the ambient air. And I haven't done the calculations. And it also depends on how good your carbon nanotubes are at absorbing long wave infrared, the thermal infrared, which we haven't characterized yet. So I think potentially, but it requires further study. That's a great point, though.
So I think that we don't have any more questions. AC says, very interesting presentation. Thank you. So,
thank you.
Well, Cole, you want to say something else? Some last words to close for the closure?
Yeah, thanks so much, Igor. and to our host Priscilla. Is learned more in this seminar than I have all week, I think. And wow, so keep up the great work over there. It's you guys are on an important mission.
Thank you, and good luck with you. Thanks for having me, and good luck with your startup university. And yeah, I'll be thinking about more problems related to Mars in the courses that I teach. I know I was asking in a class that I taught recently about whether the people who settle on Mars, what's their kind of basic mode of locomotion going to be? Are they going to walk or not? Because on the moon, you couldn't walk. Like the pendulum motion is too slow for walking. So people were hopping, right? Famously, astronauts were jumping rather than walking. On Mars, my prediction was that people would run a lot. Because if you do the analysis, there's something called the Froude number. You can calculate it, and it actually works out that for the normal locomotion speed that we're used to, running is going to be preferred on Mars than walking. So people would still walk maybe when strolling with no particular purpose, but when moving around, they probably would run a whole lot more. So I guess maybe the graduates of your university will one day get to test that prediction.
Yes, that's the plan. Yeah, we'll certainly be thinking about folks running more as well. So.
All right.
Okay.
Thanks for having me again.
Okay, thank you, Igor. Well, a very amazing topic, and yeah, I think we have a lot of discussion pending about atmosphere, so maybe we can talk about it later. And thank you very much to everything that joined us today. So, and remember, you can see the video on YouTube later. Yeah. Okay. So thank you very much, and I hope that you can join us in the next webinar.
All right. Thanks.
Bye-bye.
Good night.